this is about the results of using reinforced learning to manage the loads between the fuel cells and batteries. So it's a quite busy slide, but if we try to focus on the figure A, okay, and so in the first part we have the load profile for one voyage. Basically, that's the starting point, that's the departure of the ferry, and then transit from A to B. So basically, that's the point when the vessel arrives at the port. Okay, so that's the overall power demand asked by the propulsion system and also the auxiliary systems. So the task is really to distribute the fuel cell power and the battery power and then the shore power without knowing what's going to happen in the next time step. So in figure A, basically we have the offline optimum. So given if we know what's going to happen within this voyage, and then basically we can know what would be the best action we can control the fuel cell and the batteries. Basically, you can see the fuel cell actually tackles most of the transients. You can see the fuel cell power is kind of relatively constant. And before the vessel arrives at the port, the fuel cell will be reducing the power and then gradually shut down. Okay, and when the vessel is at the port, basically we will use the shore power to charge the battery. So that's the offline optimum you can expect using deterministic dynamic program, knowing what's going to happen across the voyage. So the next thing is basically we use different reinforced learning agents to solve the problem. In figure B, basically we can see in WQ learning, in discrete action and state space, you can see the fuel cell power is kind of following the trend as we can see for the offline optimum, but you have a lot of little wiggles happening to the fuel cell, which is not ideal. Okay, but in general, it's following the trend, but it's a bit hesitant. It's not knowing what to do exactly for the next time step, because that's the reason why you are seeing a lot of unnecessary adjustments for the fuel power. But on the other side, if we try to focus on the in figure C, using deep Q network in discrete action space, but in continuous space, basically we can see this agent is much more determined and much more confident in terms of determining what is the power going to be collected from the fuel cell and what would be the power coming from the batteries. So you can see how similar in general it compares with the offline optimum. So one thing to highlight is in figure C, actually we don't know what's going to happen. So it's almost perfect action being instructed by the deep reinforced learning agent. Okay, so that's really surprising. So basically, we can see deep reinforced learning is really good at dealing with uncertainties coming from the real world environment. Basically, we can use deep reinforced learning to deal with uncertainties coming from the environment. On the other side, because for marine applications, we do have a lot of requirements on redundancy. So basically, we try to do separate study. Let's say if we have a few cell clusters, let's say 4 fuel cell clusters, as we can see on the right side. Basically, how do we use deep reinforced learning to coordinate the operation of multiple fuel cell clusters and batteries? So basically, we can see it's not perfect, but you can see in general, the load are just kind of distributed evenly across the multiple fuel cells. On the side, we can see the continuous action space. It's not that perfect, as we have seen in the deep network, but it still is able to control the fuel cells in continuous action space. Right. So by the end, if we compare the results coming from different agents, so we evaluate the emissions and also the emission ratio compared with the offline optimum and also the cost with the offline optimum. So basically, we can see most of the agents, their performance, they are pretty close to the offline optimum. Okay, only a few percent off, which means the agents was able to learn something really close to the optimum. Okay, right. So these are the these are previous research we have done, but so we also advanced this particular work. Say we try to come up with a generic energy management framework. So that's a really early stage concept using reinforced learning to control the power systems. And then recently we have the demonstration case. So basically applying these frameworks to actual ship So basically, to guide the design of the actual ship and to design the hybrid powertrain, and also to coordinate the operation of the fuel cell and batteries. So unfortunately, we don't have that much time to go into the details, but you can find some useful insights from this paper, hopefully.